Alright, this video is about this topic called torsion theory. Okay, torsion theory. Okay, so far we have been looking at the different ways of applying loads and torques and forces onto your structures, right? So you have direct stress and strain, you have bending moment, bending stress, all this. Okay, this is also one of them. Okay, suppose you have a shaft, okay, and you decide to twist it. Okay, you decide to twist it. So let's say this is the shaft and you decide to twist it. Okay, you are actually giving a torque, right? You're giving a torque onto the rod itself. So how it's being drawn is you are doing this, applying a twisting, and this twisting force, right, is actually a torque. Okay, the torque, of course, the units is in Newton meters lah. All right. Okay, so what happens when you twist a shaft? Okay, this is what this topic is about. So imagine we need to get some parameters straightened out first. So the first one is L. Okay, L is the length of the shaft of the rod. Okay, and when you apply a twist, of course, this is your T lah. Okay, depending on what material, okay, it will have a certain nature, right? So for this we are looking at G. Okay, G, you have learned it during your stress and strain. It is the modulus of rigidity. Okay, modulus of rigidity. Different materials has different G. Okay, and this characteristic is actually how resistant is this material to shear. Okay, by shear we are talking about forces that is doing this shearing action. Okay, not the direct stress strain, is the shear stress and shear strain. Okay, so that is the G over there. So depending on what material, you have a different G. Okay, and when you do a twist, okay, you are going to turn the material. Okay, the amount of turning can be denoted by the angle. Okay, how much you twist, the angle of twist. So we call this theta. Okay, and it is in radians. Theta is in radians. All right. Depending on the shape of the rod, okay, it can be a thick shaft or a thin shaft, right? So it is going to have a J. Okay, we called it the polar second moment of area. Okay, you have learned about second moment of area in your previous topic. So this is a polar second moment of area. Okay, for a circle, right, the J, the formula is pi d 4 over 32. Okay, so of course this would be the area that you're looking at lah. So J of this area is pi d 4 times 4 over 32 to the power of 4 over 32. Okay, and very commonly the question will involve a hollow rod, a hollow shaft. Okay, which means the inside is hollow out. There's no material inside. So you're going to have this shape, right? And you're going to have an outer diameter d naught, inner diameter d out, and inner diameter is d in. Okay, under this circumstance, your J will then be pi d out 4 over 32 minus pi d in 4 over 32. Okay, or you can simplify it to, you can take out pi over 32. D out 4 minus D in 4. This will be the J for hollow rod. Okay, one very important thing to take note. Okay, a very common careless mistake that students often make is for J hollow, right? They will forget, they will write wrongly to become like this. J is equal to pi over 32. They will write D out minus d in to the power of 4. These two are different. Okay, this is wrong, this is correct. So remember, don't commit this mistake. Okay, yeah. So we got J, and yeah, so this will be typical rod J, T, L, theta, G. Okay, last but not least, R. Okay, radius. So when you look at the shaft, okay, you look at the how the rod performs at different radial location. Okay, so there is okay, never mind. So there is this thing called R. Okay, the radius of this circle. Okay, R, the radius of this circle. I will show you what this R is going to use for later on. Okay, for now, these are the key parameters. So the first formula that you will get to use is this one. T torque is equals to Gj over L theta. Okay, this one actually means for a certain angle that you twist, okay, how much torque do you need to produce that angle of twist? Okay, so let's say if I want to twist 30 degrees, okay, how much torque do you need to twist? And this one, Gj over L, you can see it depends how easy is it to twist. Depends on the material, the circle, the shape of the circle, and the length of the shaft. Okay, if you put it in the graph form, okay, if I plot torque, okay, against angle, you are going to get this straight line. Okay, this means that the more angle of twist you need to commit, the more angle of twist that you want, right, the more torque you need to produce. Okay, for a certain angle, okay, you are going to need this much torque. Okay, the higher the torque, the higher the higher your angle, the higher your torque required. Okay, and the gradient, this gradient is actually Gj over L. Okay, and if you look at it, if you compare, let's say, aluminum with steel, the G of aluminum is definitely lower than the G of steel. So what does that mean? The gradient for steel will be higher, right? So the gradient for steel will be steeper. Okay, so let's say this is aluminum. Okay, this is steel. This will mean that for a same angle of twist that I want, for a certain angle of twist, let's say this is 30 degrees, just arbitrary. So this, I need to twist 30 degrees, right? For aluminum, I only need this much torque. Okay, but for steel, I will need a much higher torque. Okay, so that is what this equation means. Okay. The other formula that is also important to you is this one. Okay, torque over J is equals to shear over R. Okay, shear. What kind of shear are we looking at? Okay, it is actually the shear that is experienced within the shaft. Okay, you see, as you twist your shaft, okay, you experience a shear across the surface of the inside lah. So imagine if I break this shaft into different layer, right? Into different layer. This one will want to turn, but this one will not want to turn, right? This piece will not want to turn. This piece will be turning. So between these two pieces, there is a shearing force. Okay, and this shear is your tau. Okay, shear force, shear stress. Okay, shear stress. Okay, and if I reorganize this equation, it actually becomes shear is equals to T over J R. Okay, how do you visualize this? It means that at the rod, for example, if I give a certain torque, if I provide this certain torque, right? Less so, which means this torque is constant, okay? And the J, which is related to the circle, is also constant, right? So these two are constant. It means this is a constant, okay? This R is actually not fixed. This R actually stands for the radius location inside the circle. Okay, how do you see it? If you look from this point of view, if I look at the shaft this way, okay, if you look at the shaft this way, okay, you're gonna see a circle, right? Okay, the center of the circle is here. Okay, so if I am interested in a location here, okay, I'm interested when the radius is this much. Okay, can you see this much? Okay, when I'm interested in the center of the circle, then the radius location is here. So this axis is R. Okay, so if you look at here, I want to know the different shear at the different location, okay, until we reach the edge of the shaft. Okay, so this is the edge. Let's call this R naught. This is the maximum radius of the circle here. Okay, so as I look along this different point, I look at this different point, the radius increases. What's going to happen? It means that as the further you go out towards the edge of the circle, the stress will be higher. Okay, the stress will increase. Means if I plot SY axis as the stress, it's going to look like this. Okay, when the radius is 0 at the center, there is no stress. There is no shear stress at the center. Okay, imagine a twist like this, there is actually no shear stress. As I go further towards the edge, the shear stress will increase more and more and more and more. Okay, and the highest shear stress, will be at this position, at the tip, at the edge of the shaft. Okay, so this is your tau max. Maximum shear stress is this much. Compared to the center of the circle. Okay, carry on from where I left off just now. I was saying, as you look at the cross section of the rod, as you look from the center towards and proceed towards the edge of the rod, the shear stress at different location along the radius is going to increase. Okay, which means at the edge of the rod, you will always get your highest shear stress. Okay, so this is what the graph is about. Okay, it's a straight line, and this is what the equation is about. Shear stress is equals to T over J times R. This value is a constant. Okay, and then you will get a distribution across the value of the radius. Okay, so this is the idea behind this equation. All right, and of course, if your rod is hollow, okay, if your rod is hollow, which are the 2 points of interest? The inner radius and outer radius, right? So this is the outer radius and this is the inner radius. Okay, there's no material in the center, so when you draw your shear stress line, you should not draw any line in this part. Okay, you should only draw one line here, because this is the only part with the material, with the shaft material. So this would be your shear stress curve, shear stress line. Okay, here there's nothing. Okay, very important. Okay, like all engineering questions, we are always interested in power. Okay, so if I know that I am supposed to provide a certain torque to twist this shaft, right, and this shaft incidentally is connected to some kind of a motor or an engine, okay, and so as it turns, how much power is required or how much power is generated. Okay, this would be omega times torque. Okay, in fact, this is not new formula lah. You know that power is force times velocity, correct? So in fact, this force, this torque is equivalent to your torque law, because torque is also a turning force. Okay, and velocity is this one. Omega is your angular velocity. Okay, so they are essentially the same. Okay, so omega would be radians per second and torque would be Newton meters. Okay, sometimes you are given your RPM value instead. Okay, the shaft is turning at say 500 rotations per minute, so you have to convert it to radians per second. Okay, how to convert? It will be 2 pi n in terms of RPM, 2 pi n over 60 times torque. Okay, last but not least, there is this aspect of a fluctuating torque. Okay, a fluctuating torque, because along with time, as you, like I say, if your shaft is connected to some generator or something, okay, this torque that is operating is always fluctuating. Okay, and in order to get the torque that you use to calculate power, you will use the mean torque. Okay, T mean. Okay, so power is omega times T mean. Okay, but when you talk about shear stress, okay, the shear stress maximum, okay, you cannot use your mean torque. You have to use the highest value. Okay, this highest value torque, T max. Okay, then you can what is this? T max over J times R. Okay, when you find shear stress, use maximum torque. When you find power, use mean torque. All right, that's the guiding principle. If you read the question, there is no mention of mean or maximum torque, then assume both to be the same. Okay, you can use the same value of torque for both calculations. All right. Now let's look at a tutorial question. I'm going to look at question 6, 9.6. I'll show you the question. Well, I have a tattered lecture notes, but this is the question. Solid shaft is to transmit 750 kilowatts, okay, at 200 RPM. Okay, the shaft cannot twist more than 1 degree. Okay, and the shaft can also not exceed the shear stress of 45 megapascal. Okay, so find the minimum shaft required. All right. So let's see what information we have. The power is 750,000 watts. Okay, your RPM is 200. Okay, our length is 12 times your diameter. Okay, G is 80 times 10 to the power of 9 Pascal, 80 gigapascal. Okay, theta max is 1 degree, but we cannot use degree, we have to be in radian. So how to convert? 1 times pi over 180. Okay, so basically it's pi over 180 radians. Okay, maximum shear is 45 times 10 to the power of 6 Pascal. Alright. So is there any mention of min and max torque? No, don't have. So we can use the same value, and we find it using this formula. Okay, 2 pi n over 60 times torque. Okay, so torque is a power 7,000. Okay, divide by 2 pi over 60 times 200. All right, let's see. Okay, you will get 35809 Newton meters. Okay, now the hint there is say there are two independent conditions. Okay, these two, I cannot exceed 1 degree, I can also not exceed 45 megapascal. Okay, in order to satisfy both conditions, what is the minimum diameter I need to use? Okay, so the advice is to look at both conditions separately. Okay, you look at maximum angle, you calculate the diameter needed. You look at maximum shear, you look at the you calculate for the diameter needed, and then we look at how it works out. Okay, so okay, first part you have, let's try to satisfy one condition first. Satisfy 1 degree, okay, which satisfy maximum theta lah. I will use the equation with theta, okay, and the equation is this one, theta G over L. Okay, so this theta is your theta max, okay, theta max G over L. Okay, so theta, okay, torque, is this value, okay, 35809. Okay, J is pi over 32 times d4, okay, equals to maximum angle is pi over 180. G is 80 times 10 to the power of 9 over L is 12 diameters. Okay, then you will lump the diameters on one side and the numbers on the other side. Okay, you are going to get, let me see, pi over 32 d4 over 12d is equals to 350,0809 over pi over 180 times 80 10 to the power of 9. Okay, you will get a d cube. Okay, let's just calculate this. 3 pi in 09 divided pi 89 times 180. Okay, times 12 divided by pi times 32. Okay, 3.135 10 to the power of minus 3 to the power of 1 cube. Okay, so d is a cube root of this value. It will be 0.146 meters. Okay, so when I satisfy my maximum angle, my diameter is this much. Okay. If I satisfy my shear stress, okay. So before I look at this condition, I just want to say this one. What does it mean by satisfy the maximum maximum one angle? It means that in order for it not to break, but with a maximum twist of 1 degree, my diameter can go as low as 0.146. Okay, if my diameter drops to 0.145, okay, my twist will be bigger, correct? Because the thinner my rod, with the same torque that I apply, my twist will be higher than 1 degree already, so I cannot satisfy. Okay, the minimum my diameter needs to be is 0.146. Okay, now let's look at the shear stress. Okay, the formula you can use is then the one related to this, max shear over R is equals to torque over J. Okay, so I'm going to shift this around. J over radius is the h, right? The radius, right, is half d, okay, 0.5 d, okay, equals to torque over shear max. Shift. So this would be 35809 over 45 10 to the power of 6. Okay, and J is actually pi over 32 d to the power of 4, okay, over 0.5 d equals to this value. Okay, so again, you're going to solve until you get a d cube, but because the top d and the bottom d cancel out, and then I'm left with a d cube over here. Same case as this one. Okay, cancel d cube is like this. Okay, so you're going to have a d cube equals to some number, and your d is going to be 0.159 meters. Okay, so what does this mean? This means that with this torque, right, as I twist the rod with this torque, okay, when my diameter is this thick, okay, when my diameter is this thick, then the shear stress experienced at the edge of the shaft will be just nice, 45 megapascal. Okay, but if my diameter goes thinner, goes smaller, sorry, with this torque, right, my shear stress will be more than 45. Okay, because the thinner your rod, the your shear stress is, you cannot hit for you will go above 45 already, because your torque is this much. Okay, now let's look at these two conditions. If I want to satisfy 1 degree twist, I cannot exceed 1 degree, my diameter needs to be this much. If I want to satisfy the maximum shear of 45, my diameter can only be this much. So what is the minimum that you can choose? Okay, the answer would be this value. Okay, because if I go any lower, your shear stress will exceed 45. So I cannot choose 0.146. I can only choose 0.159. Okay, so to put it simply, if 0.146 is chosen, tau max will exceed 45 megapascal. Okay, but if 0.159 is chosen, the theta will not exceed 1 degree. Okay, so that is the reason why our diameter should be 0.159. 159. Okay, so this is how you will handle this problem when two conditions need to be met. You need to choose the one that is the safer one, that both sides can meet. All right.